Thank you. Hi, everybody. How many sandwiches did you all eat? Hi, everybody. Hey, that's better. All right, I'm going to make you stand up and do jumping jacks in a second as well. I'm Sihota. I'm the formerly known as professional head for drainage and line side. I'm here to talk about how easy drainage is once you figured out how complex it is. Right, so basically, drainage's key purpose is to support the railway and its other major assets to perform to their optimum manner. So it's there to provide a strong backbone for the stability of the track, for stability of earthworks, signaling structures, our structures themselves by reducing scour. And it's pretty straightforward and simple, right? It's Lincoln nodes that are connected into ellipse. There's about 488,000 assets at the moment. So, just a little base of assets there. And its key purpose is to collect water from multiple inflows to a single discharge point. And that equates to one system, and we have multiple systems. So how hard can this be to look after these lovely drainage systems that we have on the railway? All right. So, sorry, I've got my slide deck and another slide deck. Okay. So, drainage and track, and actually drainage, water and track, the interactions there, the good and the bad. The bad, flooding. We do have lots of flooding on the railway. That flooding affects our track circuits, it affects track geometry, it affects wash pollution, slows its performance, a risk and environmental issues onto the railway. Flooding also affects and impacts onto as mentioned, the track stiffness and stability. What I mean by that is if water doesn't get away, water isn't very strong to hold stuff up. So we need it to get away, and when it doesn't, it creates sort of a nice spongy wet formation, which isn't great for our trains to run on. That same water flow and energy, which is within water that comes from surface runoff, it causes washouts and landslips. We are not a seismic zone area, so land doesn't move on its own. In this country, it moves because something's moving it, and that moving it is normally through saturated land and water taking it with it. We have three sources of water that comes onto the railway in the most simplest of terms. You've got your rainfall, you've got your surface runoff, and you've got your groundwater. So pretty easy, right? Just got to look after that water, take it away. Easy peasy. Ballast in its own right forms part of the drainage system as well. We can have interesting debates on that. Water, rain, goes onto the ballast, flows through the ballast, gets to the crossfalls, crosses over and goes into our pipe and pit system or into your cess drainage. So the importance of having clean ballast is also key in high-performing drainage systems. And so that's all pretty straightforward, all really easy, right? It's not very complex. So let's do a little test. Oh, come on. There we go. Right. So in 2 years, in 2 complete years, 26 periods, what do you reckon is the cost of delay costs, due to flooding? Lean, would you do the Slido, please? So I want you to, using your phones, put in how much you think in that 2-year period it cost Network Rail in delay minutes due to flooding on the railway. We did this as a word cloud, so. £10. What, £10? I said in millions. I gave you a hint. Okay. The right answer's up there. Okay. Should we close the Slido? Yep. Ooh. So, the right answer, there was some interesting ones. Some of you really, gosh, whew. The right answer was, it cost us, ready? £80,356,721 for that two-year span. So that's a lot of money literally going down the drain, pardon the pun, I got a lot of them. When you look at the CP6 expenditure for drainage CapEx, it's 250 million. So 32% of our CP6 capital expenditure was just spent on delay minutes just due to flooding. So we haven't quite got something right there, have we? And we need to have a look at that. And maybe it's something recent. Maybe this is something recently happening, and it's out of our control. So if we look back in the past to see what's happened, maybe we'll see some stuff going on in this space. I'm just going to use that. No, that doesn't work. This doesn't like me. There we go. Root cause analysis. So there are 14 incidents there, and these are all rail accident investment. Investment. Hello, you can see where my mind is in CP7. Rail accident investigation boards. There's 14 incidents there. Some of our recent big ones are not on there. And those 14 incidents, the ones with the little stars are directly track, where the track defects were accentuated due to poor drainage, lots of water in the area. Gloucester, we talked about Gloucester earlier. Gloucester's one of them. So of those 14, there are 3 specifically that are linked to track, those right there, the track defects there. But if we start going back on the left-hand side towards those things that caused the incident, be an earthwork failure, lots of earthworks, or a track defect that then led to derailment. If you start going back, there's a lot of, how do we say it? We're not learning. There's a lot of repeat recommendations that are coming out. Increased drainage rainfall. That's the one at the top with lots of circles. Sorry, the circles are every incident where that report mentioned that finding. So going back in time, and this isn't going back like since the start of time. This is good, 15 years or so? Looking back 15 years, we're not learning from our past mistakes. And so one wants to think maybe drainage isn't as easy as we thought it was. But it also could be other things that are affecting it. And maybe that's what we need to look at, is to say, well, okay, right, so we're not learning from the past, but possibly there's some other things that are impacting us. And we mentioned one of those things earlier today, and that's climate change. So looking in the past, things not so great. From now going forward, what are the things that we also have to deal with that are compounding the problems of poor drainage, and then that poor drainage causing issues on track, on the railway system, is huge. So climate change, extreme and adverse weather events, they're no longer called climate change predictions. They are now called climate change projections, as in they're gonna happen. And the current sort of reports are saying that there's going to be about 7 extreme and adverse weather events every year. And we're seeing that. We saw that last year, and I believe we saw that the year before. Those extreme and adverse weather events, by the way, are not just impacting on drainage and flooding. We're going to see more trees falling as well, which is a whole nother presentation for a whole nother time. If you asked me to talk about drainage today. So we're seeing more extreme and adverse weather events. We're going to see more intense rainfall in short periods of time, and then you're going to have sunny weather, which is the worst thing to have for drainage, because we like nice and steady drip of water. We don't like nice dry land and then flash flood and then dry land and then flash. That doesn't work. In the industry, we call it the first flush. It's the worst one. Because it takes all the debris, it gets all stuck, and that's where you have your big problems. So lovely days like today, where the sun is shining and no one's worried about maintaining drainage, when the rain falls, we got problems. So what we've got is extreme and adverse weather events, a change in the pattern of how we approach weather. And also too much or too little. We talked about desiccation. Yeah. So it affects drainage as well. It affects how our systems work. Those ditches that are unlined, they're all impacted as well. We have forgotten where our drainage assets are, and we are working on that right now to complete our asset inventory, unfortunately as a recommendation off of another incident. But we are completing that asset inventory. We're working hard, and OR are really hot on us to complete it. We are putting in about 2,000 assets into drainage every month, and we're not done. So your inventory is just going to go higher and higher and higher, and you're going to see assets that haven't been inspected or maintained before going into ellipse to have our complete inventory. We don't look at drainage as a system. We have lots of own goals. We have track drainage and earthwork drainage. I hate that term. It's just drainage. Water doesn't care. Water doesn't care what the boundaries are. Water doesn't care if it's track or earthworks. Water does two things. It follows the path of least resistance, and it flows downstream. Simple, right? I said it was easy. Drainage is easy. So what we've done is we've basically created this siloed breaks in the system. We sort out our earthworks drainage, and then all the water floods the track. And then we sort out our track drainage, and then all the water floods the embankments. And this is happening, I've seen it happen numerous times, own goals. And that's because we're not looking at the full run, and we need to look at the full run. So that's another challenge that we've got to face, is find those assets, link them all up, and understand how the run is through the railway so we can properly get the water away. We've got opposing priorities, projects that need to finish, come hell or high water. I like that term, right? High water, come hell or high water. You mean flooding? Yeah, we've got projects that are doing that now. It's not helping, guys and gals. We cannot build on soggy, wet ground. It is not good. Water is the enemy of civils. That's the old term. It's the enemy of electrics, and it's the enemy of mechanics, and it's the enemy of a lot of things. Except for people, we like water. We like to drink it. So we've got opposing priorities. We've got constrained funding, and that constrained funding is going to go into next year as well. So how are we going to sort out, how are we going to change the way that we approach drainage maintenance, track maintenance, railway system interaction with water? We need to have a change in approach into this. And that change in approach, let me just go on a little bit of footnote, is not just for drainage to do. It's Network Rail needs to look at how we do water management, and I'm going to show you a little bit about what we're doing in that space to make things better. There is a correlation between poor drainage, water management, and geometry, track faults, and defect. There is. It's hard to see. I'm not wearing my glasses as well. That doesn't help. But there are former retired TMEs who when I present, usually at PWI, they come up to me afterwards and said there were 3 things they learned about managing track geometry. The first thing was sort your drainage out. The second thing was sort your drainage out. And the third thing was, guess what? Sort your drainage out, right? You sort that out and you will have better track geometry because you created that stable ground for the track to run on. And so we've got challenges and opportunities along the way. When I said that water was more than just a function for drainage, it obviously is really important for drainage, otherwise why would you have drainage? But water interface and water management within the railway is bigger than just drainage. And it was something that we came across when we were working on again, one of the recommendations post-Carmont around drainage technical strategy. There were things we couldn't write in there because they were company-wide. And so a new strategy was introduced. It's the start of asking people to think differently about their approach to water. And so, Mark, can you cue up video, please?
To management strategy.
There we go.
This strategy is going to change our approach to water management. But before I tell you more, this is why we need it. Climate change is happening now, making the consequences of extreme and adverse weather a reality for all of us. Flooding and droughts already cost Network Rail millions of pounds a year and are only likely to get worse. From landslips to electrical failures, weather-related incidents affect the safety and performance of the railway, resulting in penalties, delays, poor environmental impacts and a disrupted service for our passengers. But we can improve. Network Rail is committed to running a reliable railway network To do this in today's world, we need to prioritise water management. This means dealing with the water that affects all of our railway assets. We need to grasp the wider challenges of water scarcity, polluted water, and the potential benefits of excess water, in collaboration with our neighbours. We've developed the water management strategy consisting of 5 principles. These are: take a holistic view, be resilient, use less and recycle, keep it clean, and unlock wider benefits. We are the first in the transport industry to develop a water management strategy. It's an opportunity for us to demonstrate our proactive leading approach. As the 4th largest landowner in the UK, we can make a profound impact. Water affects all of us on the railway. Every asset group and all life cycle activities, including inspection, maintenance, design, construction and asset management, have a part to play. We all have a responsibility and we need to start today. So, how do you make a difference? Start by engaging with the water management strategy. Go to the My Connect page for more information.
That's an internal Network Rail document, but anybody who's not Network Rail and would be interested in seeing that, I can leak you a copy, another drainage plan. So I've got loads of them. So water is bigger than just drainage. Let's bring it back to drainage and track though. So I'm going to ask a really simple question. My next slide of question is, what causes wet beds? It's multiple choice. Yep, 47 people, 50 people, 51 people. So if you're brave enough to put your hand and said who put up too much liquid before bedtime.
I still think that's a correct answer, Madam.
It totally is. They all are. Ha ha! Ha ha! Yes. Yeah, I didn't want to do E, all of the above, because then it ends up giving it away. Yes, so wet beds, the hint's in the name, wet, comes from pumping action of dynamic forces. It's basically where your train, the weight of our vehicles are hitting on a point of elasticity. Often it's the weld point, or it's a point as we enter into the tunnel portal, those points of elasticity where we've got different bases under. You either got a constructed ground or made ground or unmade ground, and you're getting these nice soft points where your train is just basically pounding the ground. Water, which doesn't leave the ballast and doesn't leave your formation, sits there. And that water forms the conduit to which the fines that are in the ballast or in the formation then are pumped up from the ballast up into the surface. And we start to see these little powder fines, which is those fines brought up by water, because they don't just magically go upwards. It's water that's bringing them up. And that's what causes your wet beds. It's the same function that creates potholes. So another thing to... Liam, can I go to the next slide? Is that okay? Yeah. So wet beds. So if you believe me, and if you don't, that's okay. Let's have a chat afterwards over a nice glass of wine after work on whether we disagree on how wet beds are created. I said that the hint's in the name, wet. And we looked back at a 5-year average. It's about 66 and a half. Let's say 66 work orders closed out every period on wet beds. So if you believe me, for the sake of the presentation, let's just say you do. So if you believe me that poor drainage, water sitting in that formation, in that ballast, is the reason we have wet beds. We are addressing a symptom and not the root cause. And we're going back over and over again to repeat wet bed locations and digging out either mechanically or manually the wet beds, putting in sand blankets and ballast, and then going back again because it's the water that's the problem, but we're not getting the water sorted out and letting that water move away. The cost of a wet bed, let's just, at a minimum, right? Let's just say if you did mechanical wet bed removal, let's just say £10,000 for possessions, right? Forget material, forget possession, forget your safe system of work and labor, just £10,000 for a mechanical wet bed removal. And it's about £35 an hour for a crew of 4 people for 8 hours for manual wet bed removal. If I add up the cost of that work over 10 years, what do you reckon that comes out to be? Because I can give you the spreadsheet later. £190 million. It's phenomenal. And yet we look at how much we're investing in drainage. You can take that 190 million and renew the drainage system in those repeat wet bed locations, and you'll stop the wet beds from appearing. We're on a hamster wheel. We need to sort of stop sometimes and just step off and say, what is happening in this area? And that system approach, holistic view of where the water's coming from and why we have a problem there. So, right, I did that one. Okay. So I'm going to go into a little bit about what's going to help us fix the drainage problems and help us to sort out, and then I'm going to show you a little bit about where you can find answers, because really I'm getting everybody depressed. I can feel it. Let's go and uplift the room and get some answers in the room. So the drainage design standard says that in order for us to properly design drainage systems, we need to understand the catchment. We need to understand the catchment and the characteristics that come in the catchment. And then for those that are really geeky, we have these models and you don't have to be geeky, I'm a geek. We have these lovely models that we could use that you run the data through in order to figure out how much water is flowing towards you. So pretty straightforward, right? Designers need to do this. Let the designers do this. They should be doing this, let me say that, right? The whole purpose of this is what we want is the fabulous value of Q. Q is discharge. Q is what we want. We want to know what the discharge is, the peak flow rate. Because once you understand what the peak flow rate is coming off the catchment, you design for that because it's your inflow into your drainage system. And what you want to make sure is that Q in equals Q out, right? Make sense? Water coming in equals water going out. How much water is coming in? I don't know, but I can calculate how much water my system can hold. So, ta-da! Don't worry, I won't quiz you. No quiz or no Slido on Manning's equation. So there's a lovely equation that those in the industry and our water people and water drainage engineers should know by heart. True ones have it tattooed in. Is Manning's equation. And we use that equation to say, right, okay, Q, right? So you need to know what Q is. This helps me calculate my Q coming in, so I know what my area is, what I need for my diameter, what I need for my gradient. Happy days. Happy days. Are we doing it? I challenge and say we probably aren't. We're probably just copying and pasting past designs. And we're not really understanding what it is that our drainage systems are capable of holding and how much they should be. Forget the demand even put onto them. How much are these drainage systems able to carry, and what's Q out? So one of the things I want to also share is, so drainage systems, right? I said lots of inflows to one outfall. You have multiple systems to multiple catchments. Catchments. They're not always one-to-one. And so the answer is, right, okay, if I can calculate using that equation what my Q out is, where do I go to find out what my Q in is? Cue next video, Mark. Is he there?
Surface water runoff has potentially devastating consequences to the railway. At Network Rail, we need to manage this threat across our infrastructure to ensure we operate a safe and reliable service. This is why dependable data is so important. It helps us to make the right decisions to protect passengers. Now, for the first time ever, we have a data set that maps rainfall catchments across the entire railway network. It's taken more than a year to produce and encompasses more than 100,000 individual catchments, taking into account various catchment characteristics, from catchment area to soil type, in order to understand potential surface water runoff. This dataset can provide the likely amount of surface water runoff flowing towards the railway from each catchment for a given rainfall event. It relies upon the Flood Estimation Handbook, an industry-standard statistical model developed to understand surface water runoff peak flows from UK catchments. While the methodologies used aren't new in themselves, this is the first time we've been able to access this information for the national rail network at the touch of a button. The dataset is available as a map layer in GeoRINM Viewer. A water threat index derived from the Flood Estimation Handbook model and other critical attributes such as crop cover and catchment slope provides a colour-coded ranking for each catchment. At a glance, the user can understand the catchments that potentially pose a surface water threat to railway infrastructure. This helps asset engineers swiftly decide which assets need improvement first and where to install new drainage systems, making budget allocation easier and enabling rapid comparative assessments of which catchments are potentially more troublesome. Now it's possible to view a section of track online and contrast the relative hazard posed by adjacent catchments and how these compare with other catchments across the network. The dataset also provides a great starting point for more advanced analysis, assisting asset management teams and designers in making informed decisions and facilitating good engineering judgment when developing new capital schemes. In addition, the dataset is also being used to build new asset management tools currently under development, such as the Streams tool. When used in conjunction with programs such as this, the dataset has the potential to help provide a complete drainage system overview from inflow to outflow. This allows engineers to understand the current and future ability of drainage systems to protect the railway in the years ahead.
Oops, sorry. Oh, the twinkly music finished. There we go. If you're Network Rail, you go into Connect, you just on the search engine, put GeoRINM Viewer. It'll come up. Everyone in Network Rail has access to it. If you don't work in Network Rail, you can ask for an output via Freedom of Information Act or any of the senior asset engineers or program engineers that work around that area. It's the first start to say how much water is coming towards us. So from a design perspective, absolutely, that's the tool that's going to help you find out what your queue is. One of the ways to find your queue is, if you're maintenance, why do you want to know this? Let's go back to me talking about wet beds and track geometry problems. Where you have those repeat wet bed locations, where you have those repeat cyclic top or twist fault problems, and you're trying to look at it going, what is causing this? It might be something like that surface runoff. You're not seeing it, but you've got lots of water flowing through that track area, and that might be where the cause is. And we've done a little bit of correlation on some of the recent major incidents we had: wing wall failures, temporary works collapses, and also looking at past incidents where we were looking at the catchments in that area. So have a look at GeoRINM Viewer. There are over 100,000 catchments there. And you can use that to inform you around the risk that surface runoff will create. And not just track, I should say. You want to put in a new substation? I would highly recommend you look at the catchment layer, because before you put in any sort of big electronics works, you need to figure out whether you're going to get a lot of water flowing towards it. The catchment layers look something like this when you go into GRV. You click on the area, you can put in an ELR, it highlights the catchment that you're in. The drainage assets are those that are shown in the link nodes. So if there are drainage assets there, it will be mapped out as well. You just click on the layer, turn them on and off. And then what you do is you click on additional information, and another pop-up will come up where it will give you the catchment ID. It shows you the Q values, and not only that, it gives you varying rainfall. So your Q med is your medium. That's the one you want to use. That's based on median annual rainfall in the past 3 years. If you're doing designs, you want to start designing for future resilience, 1 in 200, 1 in 100. And then, I don't know if you could see towards the bottom, it has CC in there as well. So that includes climate change projections on the last two as well. So I've got another question to ask you. I promise this will be the last one and I'll wrap up. So the values there are shown in cubic meters per second. How much water is actually 1 cubic meter? Just to visualize what that is when we talk about 2 cubic meters per second in surface runoff. What do you reckon? It's multiple choice again. Yep, I'll wrap that up. I tricked you again. They're all right. Yeah. 1 cubic meter of water equates to about 12 baths full of water. So when you think about that much water per second is funneling through a catchment to a point. And where's it going to go? Remember I said it's really easy. It's going to go downstream, and it's going to go downstream. It's going to follow the path of least resistance. Hopefully that path of least resistance is our nice maintained drainage system. If it's not, it's your cable troughing, it's your rock cutting, it's your ballast, right? So just taking a look at that. Please do have a look and have a play with that data. And just to sort of zoom out and show you, there are a lot of catchments. There's about 100,000 I mentioned. And you get some really big ones. The one I highlighted, the one I selected for this presentation, is quite a large catchment. And often these odd-shaped large catchments are at our favorite high-risk locations. Anybody want to have a guess what those high-risk locations would be for catchments? I don't have a Slido on this, so just yell. Tunnel portals. Tunnel portal locations are funnels for catchments. This is Huntington. We had a massive temporary roads work, washout failure, all land onto the track. Basically 2 roads worth of temporary roads material just onto the track. Luckily it was during a possession. When you look at Watford Tunnel, when we look at other tunnels, we see very similar sort of stuff. And very recently, Waller's Ash was another where we had a landslip come through. And again, through a rock cutting, when you look at those catchment shapes, they're funnel and they focus. So very huge catchment layers. Have a look, have a play. So that's the recent data that's just gone live. There's a few other things that we can do, of course, to make things better as well. Catchment communities is a new phrase. Look, it's not just for Network Rail to sort out water management problems. We need to look at our neighbours. We need to work with our neighbours. We're quick to say the farmer's field flooded Network Rail. Guess what? Network Rail flood the farmer's fields or homes as well. So we have to look at a catchment wide when we look at solutions. There's a big push for blue-green solutions, using vegetation, trees, natural resources to manage the water coming towards us. And sometimes those solutions are on the other side of the boundary. That's new for us. But can you imagine if we could slow down the amount of water coming towards us? That's going to be a massive help. Remote monitoring equipment, Trackwater are here. They've got a display there. That's one of them, but we need to have more where we're collecting those alarms and alerts for what's happening on the ground. Collection of condition data. We ask our inspectors, please collect condition data. It shows degradation. It helps us model where the problems are. It is important. It's not busy work. That condition data on our drainage assets, feeds all of our risk models, all of our whole life cost models. So it's so important that's the fuel that really runs the engines that we have. We're building a risk model to predict where we're going to have flooding, earthwork failures, and wet beds. We're getting accuracy of about 80%, which is really good. So that's machine learning and failure modes effects analysis with the University of Sheffield. And we're really wrapping that up soon to turn that into something real that we can start to share with you to say, where are you going to have problems? Competency and training is key, right? We talk about documents and we talk about technologies and tools. Forget all of that. Our people. If we invest in our people, the knowledge and the skills that our people have, you can do with less standards, you can do with less policies and procedures, because our people would understand what it is that they're trying to manage and they're looking at. And finally, and I think it was John who also had this on his slide as well, challenge, ask questions, don't accept the status quo, because it isn't easy. And it isn't just carry on doing what we did before, because that's not working and things are changing, so it's definitely not going to work going forward. So challenge, ask, why are we doing this? Why is it not like this? What's causing that? And keep asking for that, push to improve. And we will get there. So that's me. Thank you very much.